Okay, so let me make sure this is muted. Okay, it's muted. And let me share my screen. Okay, so, okay, what's happening here? Let me minimize this. Let me minimize this. Okay, all right, so let's talk about where we left off the last time. Whoops, okay, what happened here? Okay. That's not what I meant to do. Let me go back here. Okay, I have to scroll all the way down. All right, let me scroll all the way down. Apparently, I'm at the top of this chapter. Whoop. Okay, so this is where we were the last time. Oh, shoot. I'm sorry. I don't know why I keep going back to the top of the series of slides, because we covered all of this already. Okay, so this is where, can you all see my screen?
Yes.
Okay, good. All right. So this is where we left off the last time. And as I recall, we answered the first three: how to separate salt from a salt solution, a mixture of salt and sand, and ethanol and water. So I told you guys to think about this particular last one and tell me what you would do in order to separate such a mixture of oil and water. As we know, this is a heterogeneous mixture. If you try to mix oil and water, what you'll find is that the oil will settle at the top and the water will be at the bottom, all right? So how would you, anybody, how would you separate this mixture? Well, no idea. Come on, somebody must have an idea as to how you would separate this mixture. Okay, since nobody is brave enough to volunteer, let me answer that question. Basically, in the lab, we have a piece of glassware known as a separator funnel. And I'm going to, in fact, let me search online and see if I can find a separator funnel so that you know what it looks like. Okay, this thing is slow today. Okay, separator funnel. Okay, so let me choose images. Okay, so which one shall I use? Oh, let me use this diagram right here. Okay, what's going on here? Okay, let me scroll down and see. All right, let me use this here as an example. All right, so this is from a company that sells this stuff. Okay, please, could you mute your mics, please, because I'm hearing some background noise. Okay, let me try this one here. Okay, For some reason, this is not popping up to give a bit larger image. I don't know what's going on here. Let me see if it's down here. Okay, this thing is freezing up on me for some reason. Okay, I was hoping to get a larger image of this. Hold on, let me check something down here. Okay, let me see if I can get this one being larger. This would be a good example. Okay, so. All right, so this is a diagram representing what a separator funnel looks like. And you'll notice that there's a tap right here. So basically what you do is pour your mixture into the funnel, right? As I said before, in the case of oil and water, the oil will be at the top and the water will be below. And okay, what's going on here? Okay, folks, I don't know what's going on with this. Okay, let me try this again. Okay, I'm sorry, folks. I don't know why this particular image won't stay. So what I'm going to do is go back here. I'm just going to work with this, right? So as I said before, you have the oil at top, the water below. You have the tap right here, and then you have this outlet here. And what you do is put a receptacle down here, like a beaker or a flask. And all you have to do is turn on the tap and drain the bottom layer into your receptacle down here until the boundary between the two layers get to where the tap is. And then you turn it off. And that's basically it. That's basically how you'd separate a mixture of this type, which would be a heterogeneous mixture, all right? And for those of you who plan to do organic chemistry, you'll be using this piece of glassware a whole lot because this is used whenever you're trying to extract something from a solution. So for example, you might have something in the oil layer and you can extract it using water. And therefore what you do is add the two together, you mix it together, and then when you set it out, the water layer will contain whatever you're extracting from the oil layer. And therefore you can collect the water layer and then isolate the product. So that's basically how this is used, all right? So that's the fourth. Oh gosh, what's going on here? Okay. So that's the fourth problem that you were asked to look at, how you separate a mixture of oil and water. All right, so that basically represents the end of chapter 3. So what I'm going to do now is move on now to chapter 4. And in chapter 4, we'll be dealing with elements, atoms, and ions. So let's begin by defining each of these terms. Elements, and I think we talked about this earlier, but we're going to talk about it again. Elements are basically substances that cannot be broken down into simpler substances by chemical means. So all the elements that you'll find in the periodic table fits this particular description. Now, please note, it says here that you cannot break them down into simpler substances by chemical means. And the reason why I'm stressing that is because you can actually break down an element into simpler substances, but that would not be a chemical reaction. That would be a nuclear reaction, all right? So the definition, excuse me, of an element is basically a substance that cannot be broken down further by a chemical reaction, all right? Now, of course, we know that the elements are what make up all the substances that exist on Earth. And as stated here, all known substances on Earth and probably the universe are formed by combinations of more than 100 elements. Each element has a specific number that is used to identify it, beginning with the first and simplest element with a hydrogen, and that number is 1, right? And then what you'll find is that the other elements will have higher numbers because their complexity will be increasing as you go from one element to the next. Now, most substances can be broken down into 2 or more simpler substances. So for example, water can be decomposed into hydrogen and oxygen, and table salt can be decomposed into sodium and chlorine. And that's because these are compounds, all right, which are different from elements, right? But an element cannot undergo that type of reaction. An element cannot be decomposed into anything that is simpler. Now, as far as the elements are distributed is concerned, what you'll find that it depends on what you're referring to, which part of nature we are talking about. Now, if you're looking at the human body, the oxygen is the most abundant element in the human body, about 65% by mass. But in terms of the abundance in the crust of the earth, oxygen is about 49.2%. But in the universe, the most abundant element is hydrogen, 91%. And after that, the second most abundant element is helium, which is 8.75%. All right, so that just gives you an idea as to the relative percentage of the different elements that exist on the earth or in the universe or in the human body. So what we have here are 3 pie charts, which basically discuss what we just talked about, just giving you an idea as to the relative amounts of elements present in the universe up here. As we said before, hydrogen is 91% of the entire universe, but the most abundant element in the case of the Earth's crust, seawater, and air is oxygen, which is 49.2%, followed by silicon, then followed by aluminum, and then you have some other elements. And then when it comes to the human body, the most abundant element is 65% oxygen, and then you have carbon, then you have hydrogen, and then you have calcium and phosphorus and traces of several other elements. Okay, now the names of the elements. How do we arrive at the names of these elements? Well, it depends. In some instances, the name is of a Greek origin. For example, iodine comes from the Greek word iodes, which means violet, and that's because the color of iodine is actually violet. Or the name can come from some property and in some cases have a Latin origin. For example, in the case of fluorine, it comes from the Latin word, and I don't know if I'm pronouncing this right, fluor, meaning to flow, all right? And that's because there's one particular ore which contains fluorine, which is low melting, and therefore will flow under normal temperatures. And then in some cases, the origin might have some German name, such as bismuth, which comes from a German word, Weissmass, don't ask me how that works out, which means white mass. And then in some cases, the name comes from a particular location. So for example, germanium was discovered in 1866 by a German scientist, so therefore the element is named after the country, Germany, all right? And then you can have a situation where the name comes from the name of a famous scientist, such as Einsteinium, which is named for the famous physicist, Albert Einstein. All right, so that's basically a brief overview of the sources of the element's name. Now in chemistry, we tend to use symbols for the elements because it's a shorthand way of representing these elements. So whenever you see a symbol for a particular element, it can stand for the element itself, or it can stand for one atom of the element, or it can stand for a particular quantity of the element, all right? So it all depends on the context, really, all right? Now, as far as the rules for the governing symbols for the elements, basically, the symbol can have either 1 or 2 letters. If it is 1 letter, then that letter must be a capital letter or uppercase, such as in the case of hydrogen, where the symbol is H, or in the case of carbon, where the symbol is C. But if you have 2 letters, then the first letter must be capitalized and the second letter will be a common letter, such as in the case of neon, where the symbol is Ne, and barium, where the symbol is Ba, all right? So basically, any symbol for any particular element must fit either this description or this. Either it has 1 capital letter, or it's a combination of 2 letters where the first one is capital and the second one is lowercase, all right? And this is just a representative list of different elements and their symbols, right? And what you'll find is that most symbols start with the same letter as their element. So in most cases, you can actually see a correlation between the symbol and the actual name of the element, such as Al for aluminum and I for iodine. But in other cases, there's no connection, at least not in the English language, between the symbol and the name of the element. So for example, the symbol for mercury is Hg, and the symbol for silver is Ag, all right? Now, why is that so? Well, in some instances, the symbol actually comes from the early names in Latin for the same element. So for example, we mentioned mercury, where the symbol is Hg. Well, the early or former name of mercury is right here. I won't even try to pronounce it, but as you can see, one can see the relationship between the symbol and this word right here. Or in the case of potassium, for which the symbol is K, and its original name was calcium, or up here for copper, the symbol is Cu, and as you can see here, the former name is cuprum. So in some instances, the symbol that is used to represent a particular element comes from its early name, all right? Okay, so let's talk about the different categories of elements that we can identify. And it depends really again on the context and how you want to categorize them. Now, the specific type of categorization we'll be looking at is, as you see here on your screen, the categories of metals, nonmetals, and metalloids, right? So let's talk about metals firstly. So these that you're going to see here are the physical properties that are associated with metals. Metals are mostly, in fact, the vast majority of metals are solids at room temperature. There's only one exception to this, and that is mercury. Mercury is the only metallic element that at room temperature exists as a liquid, all right? But pretty much all other metals are solids under normal room temperature conditions, all right? Another property of metals is that, and I don't know if you can see the bottom part right here, it says here that metals have a high luster. In other words, they're shiny, all right? And we all know that from our everyday experience, okay? Another property of metals is that they're very good conductors of heat and electricity, okay? And then another property of metals is that they're malleable. In other words, they can be rolled or hammered into sheets, and therefore that's a reason why metals can be used to make things like engineering parts, pots and pans, and kitchen utensils and so on, all right? So these are just some properties of metals. Also, another important one here, metals are ductile, which means that they can be drawn into wires. And most metals have a high melting point, which correlates to what we said before about metals being solids under normal room temperature conditions, all right? So these are some properties of metals, and they tend to have high densities. So that's another important property of metals, all right? So those are the properties that are associated with metals. And just to give you some examples of metals, you have gold, you have iron, lead. So these are just examples of metals, all right? Now, as far as the chemical properties displayed by metals, they tend to have little tendency to combine with each other. So it is very unlikely that you'll see two metals reacting with each other to form a compound. Instead, what you'll find is that many metals will readily react with nonmetals to form ionic compounds, all right? So for example, they will combine with sulfur or with chlorine or with oxygen, and the resulting products would be the result of that type of combination. So for example, sodium will react with oxygen to form sodium oxide, for example, all right? In nature, minerals are formed by the combination of the more reactive metals with other elements. So as we said before, sodium will react with oxygen or chlorine. I think I said chlorine, but sodium chloride is actually found in nature because sodium is a very reactive element and will combine with pretty much any nonmetal. So therefore, you'll find sodium chloride in nature, for example, in aquatic environments, in seas and so on. Basically, it's a solution of a lot of ionic compounds, including sodium chloride. Okay, the less reactive metals, such as copper, silver, and gold, are typically found in a free state. So in other words, what we're saying here is that these particular elements, the unreactive elements, they tend to exist by themselves. They tend not to be combined with other elements, especially non-metallic elements. Metals can mix with each other to form alloys. Alloys are basically mixtures of metals, all right? So for example, you can have the mixture of copper and zinc. That mixture is known as brass. You can have a mixture of copper and tin, that is bronze. And you can also have a mixture of carbon and iron. Now, technically speaking, This last one is not an alloy, so to speak, because carbon is a nonmetal, but you can have that mixture which makes up steel, the mixture of iron and carbon, all right? Okay, so that's just some chemical properties of metals. Excuse me. So now we get to nonmetals. So in terms of the physical properties that they display, they're listed right here. They tend to be very dull in appearance. They tend to have relatively low melting points. They tend to have low densities. They tend to be poor conductors of heat and electricity. Now, there's one exception to this line, and that is a form of carbon that is known as graphite. Graphite is a nonmetal, but it is a very good conductor of electricity and heat, all right? And there's a reason for that, which I won't go into right now, but I just want to make note of that particular exception. Another property of nonmetals is that they, at room temperature, certain nonmetals, carbon, phosphorus, sulfur, selenium, and iodine are solids, all right? In fact, when you look at the type of nonmetals that exist in a solid state, these are the ones that we will see or observe existing in a solid state. But you have, so these are 5 nonmetals that exist as solids under normal room temperature conditions. Then we have bromine, which exists, bromine, which exists as a liquid. Bromine is the only nonmetal that exists as a liquid. And then as far as gases are concerned, we have several. We have nitrogen and oxygen, we have fluorine and chlorine. We have the elements in group 8, the inert elements, helium, neon, argon, krypton, xenon, and radon. So these elements are nonmetals that exist in a gaseous state. So we talked about metals and nonmetals, and then there's a third minority group of elements known as metalloids. And they're so called because they have properties that are intermediate between metals and nonmetals. So what this basically is saying is that in some respects, these elements behave like metals, and then in other respects, they have properties that they share with nonmetals, all right? So these are the metalloids here. There are only 7 of them, all right? And they kind of occupy a very special position in the periodic table, which I'm about to show you right here. So this is the periodic table with all the elements, and the elements in the blue boxes, those are the metals. The elements in the green boxes would be the nonmetals, and the metalloids are colored, the boxes are colored, I think it's gray. And you'll notice that the vast majority of elements in the periodic table are metals, and they tend to be to the left of the periodic table, right? In fact, there's a line right here. In most periodic tables, you'll see a thick black line, stepwise line like this, which basically represents the boundary between the metals and nonmetals in the periodic table. So the elements to the left of that line are the metals, with the exception of hydrogen. Hydrogen is the only element on this side, which is a nonmetal. And then on the right side of that line, you have the nonmetals. And then just on either side of that line, you have the metalloids, the boron, the silicon, the germanium, arsenic, antimony, tellurium, and polonium. These are the metalloids. So for example, if you look at a metalloid such as silicon, silicon is shiny, so therefore it has that particular property in common with metals, but at the same time, it is not a good conductor or as good a conductor of electricity. So that's the property it has with nonmetals. So that's just one example of a metalloid and how it, in some respects, behave like a metal, and then in other respects, behave as a nonmetal, all right? So this is one way of categorizing the different elements, but there are other ways as well, which we'll get into later on. So as stated before, the metals are to the left of the periodic table, and the nonmetals are to the right. And of course, we have the metalloids, as I said before, which are directly on one side or the other of the line, which I pointed out here. Okay, so let's talk about the fundamental particle that exists in matter, the atom, right? It's the smallest particle of an element that can exist, all right? And this is also the smallest unit of an element that can be involved in a chemical reaction. Now, people were concerned with, okay, is it possible, okay, let me go back to the time of the Greeks and so on. The Greeks back in their day were concerned about whether or not it's possible to break down substances to its smallest fundamental unit. So the Greeks had a word for that particular fundamental unit. They call it atomos, from which we get our word atom, right? But of course, back then they did not have the technology to explore the possibility of such a particle. And then Dalton's, a couple of centuries later, an Englishman, he came up with a model of the atom. So according to his theory, so Aristotle was the person who came up with the whole notion of the fundamental particle of substances. And then John Dalton, he proposed the model of an atom, which was based on basically information that he had at the time. So these are the fundamental assumptions of Dalton's atomic theory. The first of which is that elements are composed of minute indivisible particles called atoms, all right? Now, let me just say at this juncture, before I move on to the other assumptions, that we now know that this first assumption is not true, all right? We now know that the atom itself can be broken down into even smaller fragments. In fact, the atom, for most elements, can be broken down into the fundamental particles of protons, neutrons, and electrons, all right? Now, back then, Dalton didn't know about that because, of course, back then, they did not have the technology to explore the atom the way we do now. So basically, he thought at that time that the atom was indivisible, but now we know that is not true, all right? The second assumption is that atoms of the same element are alike in mass and size. The third assumption is that atoms of different elements have different masses and sizes. So basically for this assumption here, what this is saying is that if you could actually see the atoms, they will look identical. They will have the same mass and the same volume. But if you compare, in the case of the third assumption, if you compare atoms of different elements, they will look different. They will have different masses and different sizes. The fourth assumption is that chemical compounds are formed by the union of two or more atoms of different elements. The fifth assumption is that atoms combine to form compounds in simple numerical ratios, such as 1 to 1, 2 to 2, 2 to 3, and so on. So for example, in the case of the water molecule, we all know that the formula for water is H2O. So therefore, the ratio of hydrogen atoms to oxygen atom would be 2 to 1, all right? And in the case of carbon dioxide, the ratio of carbon to oxygen would be 1 to 2, and so on and so forth. So basically what the fifth assumption is saying is that the way atoms combine to form compounds, they form ratios, simple numerical ratios, whole number ratios, all right? The sixth and final assumption is that atoms of two elements may combine in different ratios to form more than one compound. So for example, hydrogen, let me get out of this here. Hydrogen and oxygen, let me open this up. Hydrogen and oxygen can combine to form two compounds. One of which is H2O, which we're familiar with, and the other one is H2O2. So this is water, and this is hydrogen peroxide. Hydrogen peroxide. These are two different compounds, even though they're made up of the same elements. But we know they're two different compounds because we know their composition is different. In this case, there's a 2 to 1 ratio between the hydrogen and oxygen. In this case, there's a 2 to 2 or 1 to 1 ratio between the hydrogen and oxygen, all right? So that's basically what the final assumption, according to Dalton, is saying. Okay, let me do this here. Okay, so that's basically Dalton's theory. And what we're looking at here are basically diagrams which further explains what we just covered. So according to Dalton, the atoms are, of course, individual particles, and atoms of each element that are alike, atoms of each element are alike, in mass and size. So if you were to look at oxygen atoms, they'll look exactly the same. And if you were to look at the hydrogen atoms, they'll look exactly the same in terms of their mass and size, all right? Also, according to Dalton, atoms of different elements will be different. They won't have the same mass and sizes. So if you compare the hydrogen to oxygen, they'll look different, right? Hydrogen, of course, is a smaller atom compared to the oxygen atom and also has a lower mass compared to the oxygen atom. Okay, now this is dealing with the fact that atoms will combine in specific ratios to form compounds. This here represents the models for the water molecule. So as you can see, for every oxygen atom present in the molecule, there are 2 hydrogen atoms, right? So there's a 2-to-1 ratio being displayed here in the case of water between the hydrogen and oxygen. And then over here in the case of hydrogen peroxide, there's a 2-to-2 or 1-to-1 ratio between the hydrogen and oxygen, all right? So that is basically what Dalton is saying concerning how the atoms combine. They combine to form compounds where there are ratios that are small, whole number ratios between the atoms of the elements in their respective compounds, all right? So as I said before, the ratio of hydrogen to oxygen is 2-to-1 in the case of water, but in the case of hydrogen peroxide, the ratio is 1-to-1. Okay, so let's talk about the composition of compounds. So there's a law called the law of definite composition. And what this law says is that a compound always contains 2 or more elements chemically combined in a definite proportion by mass, all right? So basically what this is saying is that any compound that you can identify, if you were to break it down into its constituent elements, what you'll find is that the percentages of the elements will be fixed. And it doesn't matter where the compound comes from, it's the same compound, then that's basically what will exist, a fixed relative proportions of the different elements present in a compound. Now, the example that we're looking at here is the example of water. If you break down water into its constituent elements, you'll see that 11.2% of it will be hydrogen, and the rest, which is 88.8%, will be oxygen, right? And as stated down here, water always has these percentages, all right? If the percentages were different, then the compound would not be water. Very important for you to recognize it. So if you have a compound which is made up of hydrogen and oxygen, but the percentages are different, then you know that your compound is not water, because water has the percentages of 88.8% and 11.2% oxygen and hydrogen, respectively. Now, in the case of hydrogen peroxide, the percentages are different, right? In the case of hydrogen peroxide, the percentage of oxygen is 94.1%, and the percent of hydrogen is 5.9%, right? Again, hydrogen peroxide has these percentages, and if the percentages were different, then you know that the compound is not hydrogen peroxide, all right? So that's basically how we, one of the ways we help to identify a compound. We look at the percentages, but that's not the only way, but that's one of the things that we look at whenever we're trying to identify a particular compound. We look at the percentage by mass of the different elements in that compound. Okay, now there's a law known as the law of multiple proportions. I don't think it's in your textbook, but I thought it was important for me to go into this law. And this law says atoms of 2 or more elements may combine in different ratios to produce more than one compound. And we see that in the case of hydrogen and oxygen, right? So, I'm sorry, in the case of water and hydrogen peroxide. Now, in the case of water and hydrogen peroxide, they're made up of oxygen and hydrogen, but their percentages are different. Now, let's see what happens if you keep the mass. Let's say you get 2 samples of one each of water and hydrogen peroxide, where the mass of hydrogen is fixed in each case. If that's the case, then what you'll find is that the mass of oxygen in the case of water is 8.0 grams, and the mass of oxygen in the case of hydrogen peroxide is 16.0 grams, right? And you'll notice that the ratio between the oxygens in both compounds is a simple ratio of 2-to-1, which makes sense if you think about the formulas, the respective formulas of water and hydrogen peroxide. Because if you go back to this diagram here, or this formula right here, you see that if the hydrogen remains fixed, we have 2 hydrogen atoms in the molecule here, in the case of water, and 2 hydrogen atoms here in the case of the hydrogen peroxide molecule, you see that the ratio of oxygens between the hydrogen peroxide and the water would be 2-to-1. So that's a reason why we have the 2-to-1 ratio here in the case of comparing the 2 oxygens between the hydrogen peroxide, and water where the mass of hydrogen is fixed. Okay, so as stated here, the 2-to-1 ratio is basically calculated by dividing 16 by 8. Okay, therefore, hydrogen peroxide has twice as much oxygen by mass as does water for the same mass of oxygen. And that is reflected in the formula, as I said before, when you compare the formula for water and the formula for the hydrogen peroxide molecule. And there are some other examples of different compounds made up of 2 or more elements, such as in the case of copper 2 and copper 1 chloride, right? As you can see here, the composition will be different. In fact, these are the percent composition of the 2 elements in the separate compounds. So what that means is that they're 2 different compounds, basically, even though they're made up of the same elements. Excuse me. And you see a similar comparison between these 2 compounds, methane and octane, and also between methyl alcohol, ethyl alcohol, and glucose, all right? Again, you see the percentages are different in each case, all right? So it's possible for the formation of 2 or more compounds from the same elements, all right? And you know that they're different compounds because their percent compositions will be different. Okay, any questions so far? Any questions? Any questions? Okay, so as I said before, atoms can be broken down into smaller fragments. So what we'll be looking at here in this section are the different subatomic parts of the atom, the different fragments that make up an atom. So we're going to start off with the obvious fact that the atom is a very, very small particles, all right? But within the atom, there are even smaller particles. Now, just to give you an idea as to the size of an atom, we're going to look at this dot right here. So let's assume that the diameter of this dot is 1 millimeter, all right? So if you look at a ruler, you'll see what 1 millimeter looks like. Then basically, if you can literally line up 10 million hydrogen atoms across that line, across that diameter from one edge of the circle to the other, all right? So that gives you an idea as to how small a hydrogen atom is, all right? Now, in terms of the different particles, they were discovered by different persons. This guy, Sir William Crookes, he came up with an invention known as the Crooks Tube. And the Crooks Tube basically, let me see if I have a diagram of it here. Okay, so this is a Crooks Tube here. Let me just briefly explain what it consists of. It consists of a tube, glass tube that's evacuated. And you have 2 metal which serves as electrodes. There's one right here and one right here, and they're both connected to an external circuit. As I said before, the tube is evacuated, and when the circuit is closed, what happens is that you have a stream of particles coming from the negative electrode and attracted to the positive electrode. It turns out that that stream of particles have a particular property in that they are negatively charged. And later on, these particles were called the electrons, right? Now back then, and they're still called this to this day, the stream of particles in this setup is called, are called cathode rays, but they are made up of electrons. Oops, I'm sorry. Let me get out of this here. I accidentally clicked on something apparently. Okay, so when these particles were discovered, Sir Joseph Thomson, he did some experiments to investigate the actual nature of these particles. He found out that they travel in straight lines, they are negative in charge, and they are deflected by electric and magnetic fields. They produce sharp shadows and are capable of moving a small paddle wheel. And this was basically the particle which is responsible for all these properties that J.J. Thomson discovered. And the particle was called the electron, right? So this is a fundamental unit of charge which is present in all atoms. And then another person discovered another subatomic particle known as the protons, right? And J.J. Thomson jumped on that to investigate the nature of these particles, and he found out that the particle has positive charge, and therefore he decided, or he determined, that atoms contain both these positive and negatively charged particles, right? And as I stated before, this disproved the Dalton model, which states that atoms were indivisible, right? Because basically, based on the experiments done by Crooks, by Goldstein, and by Thomson, we are now come to the conclusion that atoms consist of smaller particles, which are positive and negative in nature. And in actual fact, it was discovered that the number of positive and negative particles are the same in order for the atom to be totally neutral, all right? And then in 1932, James Chadwick, an Englishman, he performed some experiment where he discovered a third particle in the nucleus, which was called a neutron. And the reason why this was important was because based on what was done before, they found out that there was an extra mass in the atoms, which cannot be accounted for by the proton and the electron combined. And therefore, that's why James Chadwick did his experiment, and he discovered the third particle, which basically explained the extra mass, right? And one particular property, well, there are two important properties of the neutron. One, it is neutral. It has no charges associated with it. And two, it has a mass which is slightly greater than the mass of a proton. So that was the discovery of the neutron, all right? Okay, so let's talk about the periodic table. Just some introductory stuff. We're going to talk about the periodic table later on, I think when we get to chapter 11 or 12, all right? But I'm just going to introduce some aspects of the periodic table. The periodic table was first designed by this guy, a Russian chemist by the name of Mendeleev. And one account that I've read about the way he went about determining or designing his version of the periodic table was that he was writing a textbook, and the textbook was supposed to be something descriptive about the elements that were known at the time. But while he was writing the textbook, he discovered that after so many elements, if you were to arrange them in order of increasing atomic mass, then after so many elements, and later on we're going to talk about what we mean by atomic mass. But basically atomic mass is basically how heavy an atom is for a particular element. So what he discovered was that if you arrange the elements in terms of their atomic masses, after so many elements, you find that the properties tend to repeat themselves. So he kind of shelved the project of writing a textbook, and he created a table where all the elements having the same property will be in one column, and at the same time, he arranged the elements in a particular row in order of their increasing atomic mass, right? So what you'll find is that the periodic table underwent some changes since he came up with his version. And one remarkable thing I must say about his version of the periodic table was that in his periodic table that he came up with, there were some gaps that were in his table which represented elements that were not yet discovered. And he was able to predict with very good accuracy the type of properties that these elements would have. For example, there is an element that we know called germanium, which was not discovered when he came up with his periodic table. He was able to predict the properties of germanium to a great level of accuracy when the element was discovered. And when you look at the properties displayed by the element, you'll see that the prediction that Mendeleev made based on his periodic table was very close to what actually the properties turned out to be, all right? And that's just one example. There are several other examples where that was the case. Now, as I said before, new elements were discovered since Mendeleev did his discovery or came up with his table. And as a result, the periodic table underwent some changes, some shifting of elements in different positions and so on. And we come up with now our new version or the most recent version of the periodic table. And each periodic table has the symbol of the element in boxes, as well as what is called the atomic number, right? And what's the atomic number? The atomic number is the number of protons in the atom of the particular element. So for example, in the case of nitrogen, the atomic number is 7. So what that means is that in every atom of nitrogen, there are 7 protons, all right? So that's the nature, well, that's basically what you'll find in most legitimate periodic tables, right? You find the symbol of the element and you'll find the atomic number. Now there's another number that you'll find, which we'll talk about later on, which is called the atomic mass, which I referred to earlier. So we need to define that later on. But before we do that, let's define first the atomic number, which we defined earlier, but we're just reiterating it here. The atomic number, which is normally symbolized by the letter Z, uppercase Z, that is the number of protons that is present, and it's located in the nucleus of the atom, all right? Then we have what is known as a mass number. The mass number is the sum of the number of protons and neutrons, which are also found in the nucleus of an atom. And the symbol that we use to represent the mass number is the letter A, all right? So if we know the atomic number, which is the number of protons, and if we know the mass number, which is the sum of the number of protons and neutrons in an atom, then the number of neutrons can be easily calculated by finding the difference between the mass number and the atomic number. Now, I want to point your attention to this representation here. In some textbooks, they call it the isotopic symbol. I'm going to explain what we mean by isotopes later on. But basically, this symbol here is a shorthand way of representing not only the element, but also the mass number and the atomic number, right? So the way we write it is like this. We have the mass number here as a superscript and the atomic number here as the subscript. And the E here would represent the symbol for the element. So for example, this representation here is showing you that in this particular atom of chlorine, we have a mass number of 35 and the atomic number of 17. And therefore, based on this representation, we can tell some things about the chlorine atom. We know, for example, that this particular atom has 17 protons, and we know that the sum of the number of protons and neutrons is 35, which means that we can calculate the number of neutrons by simply finding the difference between the mass number and the atomic number, 35 minus 17, which means that in this atom, there are 18 neutrons, all right? So in fact, okay, let me not say what I was about to say. So that's basically how we can determine the number of protons, neutrons, and electrons. Let me go back to this here and say that in a neutral atom, the number of protons and the number of electrons are the same. So therefore, in the case of chlorine, not only do we know that we have 17 protons, but we have also 17 electrons, all right? Okay, isotopes, very important term that you need to be aware of. What are isotopes? Isotopes are atoms that have the same number of protons, but different numbers of neutrons, all right? So different elements can have more than one isotope. For example, in the case of chlorine, there are two known isotopes, and I think there are others, but these are the two main ones. You have this one and this one, and you'll notice that the difference between them is that the mass numbers are different. And the mass numbers are different because the number of neutrons are different, all right? Okay, so based on the information that is provided here, we should be able to answer these questions. So let me turn it over to you. First question is, how many protons are there in chlorine 35? So what's the answer to that question? How many protons are there in chlorine 35?
17.
17. Very good. And how many protons are there in chlorine 37?
17.
17.
17, exactly. And this underscores a very important point, and that is the two isotopes are for the same element, right? This chlorine atom is chemically the same as this chlorine atom, right? Because they have the same atomic number. In fact, it is the atomic number which is used to identify a particular element. Okay, so here's another question. How many neutrons are there in chlorine 37, which is this one? How many neutrons are there?
20.
20, because of course you find that out by subtracting the 17 from the 37. Okay, very good. So that's as far as isotopes are concerned. Now, in the periodic table, the elements are arranged in order of increasing atomic number, all right? And that is different from the periodic table that Mendeleev first came up with, because back in his day, the proton was not discovered, and therefore he didn't know anything about the atomic number. Now that we know the atomic number for the different elements, based on the definition for atomic number, which is the number of protons, we can arrange elements in order of increasing atomic number. And in the periodic table that we're now using today, the elements are also arranged in columns known as groups or families. And in these columns, these elements exhibit similar chemical properties, right? So if you look at, for example, group 8, which is to the far right of the periodic table, these are the elements in that group, and they are basically behave chemically the same way as stated here. Collectively, they're known as the noble gases, or in some textbooks, they call it the inert gases, and they're all known to be very non-reactive, all right? In fact, argon, krypton, and xenon, and radon, these can react, but you have to employ some special conditions, right? And even if you have them combining with other elements to form compounds, as soon as you expose them to normal conditions, those compounds will simply decompose, all right? In the case of helium and neon, as far as I know, nobody has been able to combine these elements with other elements to form compounds, right? So these are really very inert elements, all right? Okay, let's talk about the elements in their natural states. Most substances that exist around us are compounds or mixtures. Now, there are some elements that are found in the pure form, and we call the metals, well, those elements we tend to call noble elements. We have noble metals, such as gold, silver, and platinum. These can be found in the, on Earth by themselves, uncombined with anything else, right? I mentioned these elements before. They exist, of course, by themselves. They do not combine with anything readily in nature, all right? The air that we breathe is made up of different gases, mostly nitrogen, and then oxygen would be the next gas in terms of amounts. And the form of these elements would be the forms that are displayed here. They basically exist as diatomic molecules. In other words, for every molecule of each of these gases, there are 2 atoms. So nitrogen exists as N2, and oxygen exists as O2, all right? So these elements that exist as diatomic are belong to a group of elements that exist as diatomic molecules. As stated here, a diatomic molecule contains exactly 2 elements of the same or different elements. So these elements exist in nature as diatomic molecules. And you need to memorize these, all right? You need to memorize these and recognize these elements, because this will become important, especially when it comes to certain problem-solving exercises, right? So if you see a question talking about oxygen reacting with something, then you know that we're talking about O2 and not just simply O. Or if we're referring to bromine, we're talking about Br2 and not just Br, all right? Okay, so basically when it comes to diatomic molecules, they exist as such in nature. So for example, you will never find H or hydrogen exist as a monatomic molecule. It will exist as a diatomic molecule. And the same is true for nitrogen. Okay, give me a minute here because I need to plug in my laptop. I just saw a box saying that my battery is running out of juice. 1 minute. Okay, I'm back. All right, so that's basically how these particular elements exist in nature as diatomic molecules, all right? Just some general information here about hydrogen. It's a gas that can be prepared in the lab. Typically, in the lab, we can prepare hydrogen by simply reacting an acid with an active metal like magnesium, sodium, and so on. But you can also find hydrogen gas in nature. It's in the air we breathe. And as stated here, you can also find it in volcanoes. In each of these cases, we're talking about hydrogen in a diatomic form, right? So it doesn't matter where the hydrogen comes from, it exists as a diatomic molecule, right? Oxygen is also in the atmosphere. Of course, we depend on it. About 21% of the air that we breathe is oxygen by volume, all right? Oxygen also can be prepared in a lab. In the lab, we can prepare oxygen by heating a compound known as potassium chloride. But in either case, oxygen that we're talking about here exists as O2, a diatomic molecule. All right. Okay, now here we're going to talk about the difference between the elements that exist in a compound and the element that exists by themselves. So we know that water has a formula H2O, right? It's very important that you recognize that the water that we're talking about does not have any free hydrogen or free oxygen. What you have in water is hydrogen combining with oxygen in a particular proportion, 2 to 1, all right? So the H2 part of water means that there are 2 atoms of hydrogen combined with 1 atom of oxygen in the water molecule, all right? So this here represents the structure of hydrogen, H2, the diatomic molecule. This here represents the diatomic molecule, oxygen, but this here represents the structure of H2O. As you can see, even though we're talking about similar elements in the case of water compared to these two, the combination is different. So therefore, the water here is a completely different substance compared to the oxygen and the hydrogen from which it is formed. All right. Okay, so let's talk about compounds. We talked about elements earlier. In the case of compounds, we said that a compound is a substance that can, well, I don't think I said so. Let me just say it now. A compound is a distinct substance that contains 2 or more elements combined in a definite proportion by mass. Another way of defining a compound is that a compound is a substance that can be broken down into simpler substances by chemical means, as stated here, all right? Elements, on the other hand, cannot be broken down into simpler substances by chemical means, right? So basically, in a particular compound, what you'll find is that the ratio of the different atoms or the atoms of the different elements will be a small whole number ratio. So it could be 1 to 1, 2 to 1, 1 to 2, etc. So you'll never see a fraction of an atom present in a particular molecule. Now, when it comes to the different types of compounds, there are 2 broad categories. You have molecular compounds and you have ionic compounds. So let's talk about the difference between a molecule or a molecular compound and an ionic compound. A molecule is the smallest uncharged individual unit of a compound formed by the union of 2 or more atoms, all right? So basically what you'll find in a molecule is a collection of 2 or more atoms that are held together by some forces known as covalent bonds, right? So a water molecule, for example, will consist of 2 hydrogen atoms and 1 oxygen atom, and they're held together as a unit, all right? And that is true for pretty much all molecules. Now, if you were to break up this molecule, then basically this substance will not be water anymore, and basically you're going to end up with the elements hydrogen and oxygen formed. And this can be accomplished in the lab if you perform an experiment known as electrolysis, where you pass an electric current through the water and you're going to end up with hydrogen and oxygen gas being produced. Ionic compounds, on the other hand, are different. An ion, let's talk about what we're talking about here with respect to ions. An ion is a positively or negatively charged atom or group of atoms. Now, there are 2 types of ions. You have the positively charged ion, which is known as a cation. And we have some examples here, or one example here. For example, the sodium ion, which is positively charged. And then we have an anion, which it would be the negatively charged ion. For example, the chloride ion would be an example of an anion. So in the case of an ionic compound, what happens is that you have the cations coming together with the anions, and there'll be a very strong attractive force between these ions because they are oppositely charged. And the result would be a very, very strong, what we call ionic bond. And as a result, you're going to end up with your compound being ionic. Now, here's an example of an ionic compound, sodium chloride. Sodium chloride is made up of 39.3% sodium, and the rest would be chlorine by mass. This compound does not conduct electricity, and that's because the ions will be in a fixed state. Now, let me just say this. You may or may not know this, but in order for an electric current to pass through any substance, you need charges that are mobile, that can move. In the case of an ionic compound, that's not the case in the solid state. The ions are basically stationary. Now, if you melt it, then the ions will be more mobile, and therefore you can pass an electric current through it. And when that happens, a reaction will take place where sodium and chlorine will be formed as a result, all right? So we call this electrolysis, where we use an electric current to break up the sodium chloride into its constituent elements, all right? Okay, so as stated here, the particles of sodium chloride are positively charged and negatively charged. The sodium ions are positively charged and the chloride ions are negatively charged. And as a result, you're going to have a strong attractive force between the ions. Now, in terms of the gross structure of sodium chloride, it's going to look something like this. Now, these are two representations. This is a space filling model, and this is just showing you the positions of the ions with respect to each other. So we call this the crystalline structure of sodium chloride. And as you can see, it's basically an arrangement, a very ordered arrangement that simply goes on and on and on throughout the structure of this particular compound, all right? And in fact, you can identify what is called a repeat unit. In other words, a unit that repeats itself over and over again throughout the structure, all right? And that's all I'm going to say about this. If you do general chemistry 1, we're going to get into this in more detail. Now, let's talk about ionic compound formulas. So basically, when we talk about the formula for an ionic compound, what we're talking about is a formula that expresses the smallest whole number ratio that exists between the cations and the anions. In other words, we're talking about the empirical formula for the compound. So key thing you need to remember here is that unlike in the case of a molecular compound, there's no such thing as a molecule that exists for ionic compounds. So in the case of sodium chloride, for example, there's no such thing as a molecule of sodium chloride. This formula does not represent a molecule of sodium chloride. This formula represents the smallest whole number ratio between the sodium and the chloride ions in the compound. In other words, it's sodium chloride, NaCl, a 1-to-1 ratio between those two. So that's a point being made here. The formula NaCl means that the ratio of sodium to chlorine or chloride is 1-to-1. So if you look at the structure here, if you count up all the sodium ions and all the chloride ions, you're going to see it's a 1-to-1 ratio, all right, as stated here. So for every chloride ion, there's a sodium ion in the structure. Okay, so what we have done so far is talked about the different types of compounds. There are two types. You have molecular compounds and you have ionic compounds. The molecular compounds are basically consisting of discrete units of molecules, which are made up of atoms of 2 or more elements, whereas in the case of ionic compounds, you have cations, which are positively charged, anions that are negatively charged, and you don't have any molecular units. Basically, the formula for ionic compounds will be a simple whole number ratio between the cations and the anions. Another difference between molecular compounds and ionic compounds is that molecular compounds, the atoms are held together by what are known as covalent bonds. We're going to talk about the nature of these bonds later on. Whereas in the case of ionic compounds, these are held together by ionic bonds, which would be the result of very strong attractive forces between the positive and negatively charged ions. Okay, I think this is going to be the last thing we're going to discuss, chemical formulas. In chemistry, we use chemical formulas as a shorthand way of representing a compound, and it can serve several purposes. For example, it can serve as an abbreviation for the names of compounds. So for example, this here represents the compound calcium chloride, all right? But a chemical formula can also give you the composition in terms of what makes it up in terms of atoms and ions. So for example, you know that in this compound, it consists of calcium and chlorine as the elements that make up that compound, all right? It can also give you the ratio of the different atoms or ions that are present. So for example, in this particular compound, there's a 1-to-2 ratio between the calcium ions and the chloride ions, all right? Which is what is shown here, 2 chloride ions for 1 calcium ion. Okay, so let's talk about the rules for writing chemical formulas. Basically, when a formula is written, we write the symbol of the element that represents 1 atom. Now, typically, we don't use number 1 as a subscript to indicate the number of that 1 atom, right? We just simply write down the symbol of that element without the number beside it, all right? So for example, in the case of NaCl, we understand, based on how this formula is written, that there's 1 sodium ion and 1 chloride ion represented in this formula, right? We don't need to put the 1s here and here, all right? Now, if you have more than 1 atom of an element in the formula, then we write that number beside it to the right as a subscript. So for example, in the case of this molecule here, this 3 indicates that there are 3 hydrogen atoms present. We have 1 phosphorus atom present here, and here we have 4 oxygen atoms present, all right? So that's how we represent the number of atoms for the elements present in a molecule. We simply write the number of atoms to the right of it as a subscript to indicate the number of atoms present in either the molecule or the formula unit of the compound. When you have a formula containing more than 1 group of atoms that occurs as a unit, then we place parentheses around the group, and the number of units of that group is placed outside of that parentheses to the right as a subscript. And later on, we're going to see a lot more examples of this, but let me just show you this one example here. So in this case here, we have 3 barium ions represented here, and you'll notice that you have PO4 within the parentheses here, and you have 2 outside as a subscript. So this 2 here basically multiplies everything within the parentheses here by 2. So basically in this formula unit here, we have a total of, well, this is called a phosphate group. And in this phosphate group, each of them has 1 phosphorus atom and 4 oxygen atoms. So therefore, because we have a 2 outside here, that 2 multiplies everything here. So basically, one can interpret this as 2 phosphorus atoms and 8 oxygen atoms within a formula unit of this particular compound. All right. Okay. So we have these examples. Formulas written as H2O, H2SO4, and the rest of them show only the number of atoms of each element present in a compound. The important thing you need to recognize is that they do not show how the atoms are combined with each other. In other words, you don't know, or you cannot tell just simply based on the formula how the atoms are linked to each other, all right? So the point here is that there's some limitation in terms of the representations of the chemical formulas. All they tell you is basically the composition, the different elements that make up the particular compound, but it doesn't tell you exactly how the atoms are connected to each other in each case, all right? Okay, so that basically represents the end of this chapter. Okay, why did that happen? I don't know. Chapter 4. Now, before we leave for today, a couple of things I want to say. Let me go to the Canvas shell for the course. So basically, let me go to assignments. And what I'm going to do now is go to chapter 4. And there's one assignment for chapter 4. So what I'm going to do is publish that folder. And I'm going to set the deadline date. Okay, so let me go here. Hold on. What assignment number was that? Okay, let me go back to files. I think it's assignment 6. I just want to make sure. Here. Chapter 4. Assignment 7. Okay, my bad. So I'm just going to change this to assignment 7. And I'm going to make this due on Friday. Okay, so Friday will be the 3rd. And I'm going to make sure that it's published for one. And let me make sure also that you're going to be able to upload. Okay, you're able to upload it. Okay, so that will be due on Friday. Now, speaking of uploading assignments, I've noticed in the assignments that I've tried to print and, well, download and print, that some of you typed up your assignments instead of using, instead of writing it in longhand, which is what I require. So please write your answers on the assignments and then you scan it, save it as a PDF document and upload it. Again, well, not again, but also some of you uploaded JPEG files or PNG files, which I specifically said that you should not do, all right? The reason for that, as I said before, is that for some reason, Canvas makes it very difficult to download it. So please make sure that you scan and save your documents as a PDF document and then you upload it into Canvas, all right? One more thing I want to make an announcement about, and this is not related to this class per se, and that is that I want to invite you, if you're interested, to become a member of the STEM Club. The STEM Club, STEM of course stands for Science, Technology, Engineering, and Math. And this is a club that was formed about a year, well, more than a year ago, just before the pandemic hit. It's a club that is trying to introduce its members to different STEM fields so that you can consider a career in these fields. I know that most, if not all of you, are probably considering going to medical school or pharmacy school, but there's also the possibility of pursuing careers in the sciences or in engineering or in math that can be just as rewarding as in medicine and other fields. And also very lucrative too, in terms of if you're just concerned about pay and all of that. So I want to invite you to join this club. The next meeting, I think, is Monday of next week. I could be wrong, but I'll let you know. But if you're interested, please let me know. And you can let me know by simply sending me an email in Canvas. And what I'll do is add you to the Canvas shell for the club, and you'll have access to all the information there. I would say that it's a worthy group to be a part of because there are several activities that we have planned, which include tours and trips, field trips to different facilities. We'll also have speakers to come and talk about their careers in their particular STEM field, and so on and so forth. So I think the first event that we have planned is a talk by one of our professors, Steve Schenk. He's going to be talking about COVID, the virus, and related topics. So I would strongly recommend that you join this group if you're interested in the STEM fields. So as I said before, if you're interested, please just indicate your interest by sending me an email about your interest in joining the STEM club, and then I'll add you to the Canvas shell, and you will be able to keep up to date with all the events and activities and meeting times and so on, all right? So that's basically it. I don't know if there are any questions you guys have. Well, you have 1 minute to ask your question. Oh, wait a minute, I see a question in the chat, or can I talk to you really quick after class? Well, it would have to be real quick because I have a class like in the next 15 minutes, all right? That is, who's this? Rosiana Bizram? Okay. Yes, you can talk to me, but you're gonna have to be real quick because I have to prepare for my other class. Oh, okay, so somebody's saying, what if I don't have a printer? My understanding is that there's a scanner that should be available in the library. Now, another thing that I'm aware of, I think I've done this once, there's also an app that you can download that you can take a picture of your document and it will save it as a PDF and then you can upload it into Canvas, all right? So that's basically how that works. So that's one avenue you can pursue. And this is to Elijah Jackson. And I see another question being asked by Alexandra. I don't know if I'm pronouncing this name correctly, Paddy Foat. How quickly do you typically respond to emails? I try to respond to them during the weekdays. I try to respond to my emails once in the morning and once in the afternoon, and maybe in the evening if I'm up to it, if I'm not too tired. So if you send me an email this evening, then definitely by tomorrow morning, I'll be able to see it, if not this evening, all right? Okay, and Alyssa Fagello is asking, so you want us to print it out, handwrite the question, then scan it and save it as a PDF? Yes, and then you upload it into Canvas. All right, any other questions? Okay, if there are no other questions, then that's it. Ms. Bizram, I don't know, do you want to talk to me now over Zoom? Hello, Ms. Bizram, Rosiana? Okay, we could do that right now, but like I said, you have to be quick about it because I have a class right now, well, at 5:30. Okay, so let me stop sharing. Let me see here. But I don't see her, she's gone.
Hi, can you see?
Oh, there you are, okay. Yes, ma'am.
Okay, so I just wanted to talk to you really quick about, and this is kind of weird to talk about like on this live, but it's just about my grade.
Okay.
Because I went over like some of the stuff I did wrong, and I got like a lot wrong on a couple of on like the first assignment, but I realized what I did because like I went through it.
Mhm.
And is there a way for me to like resubmit it or like something
So
like
what
that?
did you get wrong?
Like whenever I was doing the scientific notation, I like reversed. I did the first half right, but then I did the second, the bottom part.
I think I remember grading your I think now that you mention it.
Yeah.
I think I remember.
And I was like, oh my gosh, why did I get that grade?
Oh,
and
okay.
then I was like, I looked back at it and then.
All right, tell you what, you can redo it, but instead of submitting it in Canvas the way you did, you can email it to me as an attachment.
Okay.
All right.
Cool.
Do it as soon as possible too, because I'm trying to return your graded work to you guys. So.
Yeah. And one last question really quick, so I know you have to go to your other class, is that, so if I need to like check my work, because I was so confident when I turned that in, because I've like done it before with my other chemistry class, and I was like, oh my God, I can't believe I got that. But is there a way for me to like check it before I turn it in and get like,
oh yeah, you can. Yeah, what I mean, you know, if
can I like email it to you before I like submit it or something?
I'm not sure about emailing, but you could call me on Skype during my office hours and ask me questions.
Okay.
Right? I think I prefer that.
Perfect. Yeah, that works. That works.
Right?
That works. All right. Thank you.
All right. Take care.
Okay. Have a good one.
You too.